Hey everyone, and welcome to this QandA Help Explainer. If you were prepping for your WAEC, JAM, or NICO exams, you are in the exact right place. Today, we're diving straight into a classic physics problem, WASSCE Physics 2026, question 10. We're going to completely demystify exactly what happens inside an electric cell. Let's get right into it.
All right, so here is the exact question you might actually see staring back at you in the exam hall. It reads, the lost volt of a cell is the potential difference across A, the terminals of the cell, B, an external resistor, C, the internal resistance of the cell, or D, a voltmeter. Now, truly understanding what this question is really asking, that's the key to unlocking the right answer, and honestly saving yourself some precious time on exam day.
So, what does this actually mean? Well, in a perfect, magical textbook world, a battery or an electric cell would give us every single drop of its electrical energy. But as you know, real cells just aren't perfect. They have this inherent resistance built right into their very materials, which we call internal resistance. We represent that with a small letter R. And because of this built-in resistance, when current flows, some voltage gets used up just trying to push the current through the cell itself. That used up voltage, that is literally exactly what we call lost volts. To make this super clear, let's picture this with a really simple analogy. Imagine water flowing through a regular pipe. You start with this total massive water pressure at the pump. But as the water travels, it rubs against the rough inside of the pipe, right? That friction causes some of the pressure to just be lost before it even reaches the end of the line. So only the remaining pressure is actually useful to you. Well, an electrical circuit works the exact same way. The total electrical energy, or the EMF, is like that total water pressure. The friction inside the pipe, that's the cell's internal resistance. And the pressure lost to that friction is our lost voltage. What finally makes it out to power your actual circuit is the useful terminal voltage. Okay, so how do we actually calculate these lost volts? It's honestly super straightforward. Let's break it down. Step 1, you just identify the current flowing through the cell. That's our capital I. Step 2, you identify that internal resistance we were just talking about, the small r. And finally, step 3, you literally just multiply them together. Current times internal resistance equals the lost volts. So in physics terms, lost volts equal I times R. It's just the voltage dedicated solely to overcoming the cell's own internal hurdle. So how does this build into the complete big picture of the cell's energy? Here is the full formula you need to know. V equals E minus IR. Let's unpack that really quickly. E stands for the total electromotive force. That is the absolute maximum energy per unit charge the cell could possibly provide. But as we just learned, we don't get to keep all of it. We have to subtract the IR, which are those lost volts we just calculated. And what's left over? That's V, the useful terminal potential difference. It's what actually gets delivered to the outside circuit to do the real work. All right, armed with that knowledge, let's jump back to our exam options and systematically knock out the wrong ones. Option A suggests the lost volt is across the terminals of the cell. But wait, we just learned that the voltage across the terminals is the useful terminal potential difference, not the lost part. Option B says it's across an external resistor. Nope, again, that's where the useful voltage goes to do things like light up a bulb. Option D mentions a voltmeter. Well, a voltmeter is literally just an instrument used to measure voltage. It certainly doesn't cause the lost volts. And that leaves us with option C, the internal resistance of the cell. Because, as our formula showed, I times R, the potential difference across the internal resistance, is the absolute exact definition of lost volts. So the whole thing points us right to the correct answer. For WASSCE Physics 2026, question 10, it is absolutely option C, the internal resistance of the cell. Once you understand that lost volts is literally the potential difference across the internal resistance given by that formula, lost volts equals IR, you can confidently select this answer without even a second thought. Now let me give you a quick cheat code for the exam hall. When you're sitting there and the clock is ticking down, you need quick mental triggers. So whenever you see the phrase lost volts or voltage lost inside the cell on a test, I want your brain to immediately scream internal resistance. Seriously, linking the word lost directly to internal resistance is going to save you so much time on future exams. It's a tiny phrase, but remembering that lost inside the cell means internal resistance is a real game changer. Okay, let's do a lightning fast recap just to make sure this is absolutely locked in your brain before we do a little active practice. Number 1,
Real cells are not perfect. They possess internal resistance, small r. 2. When current, capital I, flows through the cell, it has to pass through this resistance. 3. The potential difference required to cross this specific hurdle is I times R. 4. This IR represents our lost volts, and therefore, point 5, option C is the only logical choice. All right, time to put you on the spot. Let's put this fresh knowledge to the test with a quick active recall quiz. Imagine a cell has an internal resistance of 0.5 ohms, and it supplies a current of 2 amps. I want you to calculate the lost volts right now using our formula. Lost volts equals IR. Go ahead, do the mental math. What do you get?
Boom! Did you get 1 volt? If so, absolutely fantastic. Let's walk through that simple substitution together, just in case. Our current, I, is 2 amperes. Our internal resistance, R, is 0.5 ohms. When you multiply 2 by 0.5, you get exactly 1. So this specific cell loses 1 volt internally just pushing the current through its own messy materials. It's literally that simple.
Okay, let's try just one more to really cement this. Quick quiz 2. A cell has a total electromotive force of 12 volts, and it loses 2 volts internally. Find its terminal potential difference using our full equation, V equals E minus IR. Think about what we are starting with and what is being taken away. And the answer is 10 volts. Let's look at the logic here. The cell starts with a total electrical energy potential, its electromotive force, E, of 12 volts. But as we know, 2 volts are lost internally. That's our IR. So by taking the total 12 volts and subtracting the 2 volts lost to that pesky internal resistance, the useful terminal potential difference remaining for the outside circuit is exactly 10 volts. So that brings this explainer perfectly full circle. Let's look at our final answer for WASSCE 2026 question 10 one last time. The lost volt of a cell is the potential difference across the internal resistance of the cell. Option C is for sure the correct answer. You now not only know what the answer is, but you deeply understand the why behind it, the formulas that prove it, and the analogies that just make it make sense. Listen, if you found this helpful and want more in-depth explanations exactly like this one, you have got to head over to QandAHelp.com. QandA Help has literally taken thousands of scattered past questions and turned them into a beautifully organized, reviewer-checked library covering WAEC, JAMB, and NICO across all subtexts. Don't forget to subscribe to our channel for more updates and explainers. But before you go, I want to leave you with a question to chew on. If a cell's internal resistance naturally increases as a battery gets older and degrades, what do you think happens to the lost volts over time, and why does your flashlight eventually go dim? Think about it, keep studying hard, and I will see you in the next explainer.